All right, we're just going to finish up with an example that kind of seems like it might not fit in uniform circular motion because it's not a uniform circular motion question, but it does tie in nicely to Newton's law of universal gravitation. So that's why we're doing it right now. So we're not going to use radial coordinates. It's just a straight up force question using Newton's law of universal gravitation. So here's the thing. Here's the situation. You have a classic billiard ball problem, and we're going to look at a top view of the situation, and you're looking down on the table. And then we'll call it a frictionless table because that'd get too nasty if you put friction in there. So here's the situation. I'll explain the picture first. You have like a cue ball right at the origin, we'll call it the blue one. Then you have some ball, the purple ball up here, and you have a red ball right here. And the purple ball is 1 meter away from the origin. The red ball is 2 meters away to the right here from the ball at the origin as well. So some things about this billiard ball setup, and billiard balls, pool, whatever you want to call it. Mass 1, mass 2, mass 3, I'm just going to call them equal to 1 kilogram. That'd be pretty heavy billiard balls because it's 2.2 pounds, but let's just keep the numbers nice. And the R between ball 1 and ball 2, so ball 1 is right here, and ball 2 right there, I'm going to say it's 2 meters. And if you said, I said R1, 2, if you said R2, 1, technically not wrong. I actually whited it out because I wanted to be consistent the whole way through the problem, so it's not R12, it's the separation between ball 1 and ball 2, from 1 to 2. And it's from the center of mass to the center of mass. The separation from ball 3 to ball 2, 3 to ball 2 right there, is 1 meter. It's not R32, it's the separation whoosh, just like that. And then what they're going to ask you for, what's the net gravitational force on the ball at the origin? And you can kind of picture this, right? Anything with mass has a gravitational pull. So this red ball, he has mass. This red ball has mass. The blue one has mass. So this red ball is pulling this one to the right. But at the same time, this purple ball is pulling on the blue ball. As the red ball is pulling it to the right, the purple ball is pulling the blue ball up. So you can picture the motion. This ball is getting pulled right and up, just like that. So it's going to be in the first quadrant somewhere right here. And if we're thinking about Newton's law of universal gravitation, we know that mass has an impact, but the cool thing is the mass of all the billiard balls is the same. So 1, 1, 1. So we know that's not going to be a factor. I did that on purpose because I didn't want to get it too confusing. But we do know that this ball right here, ball number 3 up here at the top, is only 1 meter away. So we know that that's half the distance. So ball number 3 actually has a bigger force pulling on the blue one at the origin here because it's closer. And if you wanted to understand this, it's half the distance of that one. So, you know, like we talked about, if you're half the distance of it, you have quadruple the force. So it's actually, even though it's the same mass, it's pulling with 4 times the force as the red ball. All right? So before you're like, Laurent, I'm getting confused. Step 1, we drew a picture. Step 2, we're going to draw an FBD on the ball at the origin right here. So we're going to go down here, I had a little scratch out there with the white out. So the ball right here at the origin, we're going to draw FBD. The force gravity of ball 1 on ball 2, so ball 1 is pulling ball 2 to the right, is just this red arrow right here. And the force gravity of ball 3 pulling on ball 2 at the origin is the upward arrow right here. So those are the only 2 forces acting on the blue billiard ball at the origin. All right, so we have that going on. And remember, we always add vectors from tip to tail. Like, I know we always draw them like this, coming out of the object like that, if we had a dot. But you can kind of picture, like, I'll go down here, this ball is getting pulled to the right and upward. So the overall motion is going to be up and to the right in quadrant 1 right there. I'm going to explain that more in a second. Step 1, we drew a picture. Step 2, we label our forces. Step 3, we're just going to go with the traditional XY coordinate system. And the reason being, we're not doing any uniform circular motion. We're not going in orbits. It's just a top view of a force problem. And we're going to use Newton's law of universal gravity. And you're like, whoa, Laurent, why have we not taken into account gravitational forces of other objects pulling on them in our whole problems before? When you get to your final answer, you're going to realize how small the force is. And you're like, oh, that's why we kind of ignore the different, like right now I'm sitting at my desk, I have a computer, I have a bottle of whiteout, as you can see. Those all have gravitational forces, and I don't notice them because you'll see how small, force gravity is the weakest of the 4 forces. And so we generally don't do questions like this because it's so small, it's negligible. All right, so step 1, we drew a picture. Step 2, we label our forces. Step 3, we're showing our coordinate system right there. Step 4, you know what we have to do, we have to sum our forces. So we're gonna sum our forces in the X, and the only force acting in the X, you have ball 1 here pulling on ball 2, and it's pulling to the right because we're doing it from the blue billiard ball's perspective right here. So this ball feels like he is being pulled to the right. So this ball feels like it's getting pulled to the right. So that's why I can put a positive right here, because that billiard ball is getting pulled to the right. And we set it equal to M2A because, you know, ball 2, that's who we're talking about right here. So we say that ball's mass times acceleration. One thing in the question, it's not even asking us for the acceleration, so I'm not even going to have to dig into this deeper. I'm not going to solve for the overall acceleration. I could if I wanted to. I could find the acceleration x and the acceleration of the y and draw a triangle and find the hypotenuse. But we're not going to do that. We're just going to find the force right there in the x direction, and that's the only force acting. We'll play the same game in the y direction. So ball number 3 here is pointing up on ball number 2. So there's some gravitational force, and I should call it FG, force gravity between ball 3 and ball 2. And once again, since we're summing the forces on ball number 2, that's who we're summing the forces on, we set equal to M2A, just like that right there. And now you use our formula. We're like, okay, big G, M3 on M2 divided by, and this looks a little confusing, it's the separation between those two billiard balls squared. And people are like, what the heck, R32 squared? Nope, it's the separation between ball 3 and ball 2, and whatever that separation is, we're gonna square it. People tend to forget the squared, and then they get it wrong. That's why it's so important to show your steps to success, because you'll get all the partial credit, you'll just lose the answer point if you forget like a math step. So don't ever lose sight of what's happening here. The billiard ball at the origin, the blue one, is getting pulled to the right in the x direction, and it's also getting pulled up in the y direction. So the overall motion is gonna be to the right and up. And I tried to color code these because the red arrow right here, we know how strong that is. It's GM2M1 over R12 squared. I didn't even plug numbers in, that's the magnitude of the force right there. And we know how strong it's getting pulled upward. It's GM3M2 over R32 squared, that number right there. So if you're like, whoa, you kind of lost me, these numbers come from our force equation. You figure out how much force is felt in the x direction, pulling to the right, how much force is felt in the y direction, pulling the billiard ball at the origin upward. And you're like, wow, this seems very familiar. We add a vector from the tip of this one to the tail of that one, and we draw our overall resultant right there. And what gets people is when they plug the numbers in the equations. That's why I did it just in variables, because that's the concept right there. It's the Newton's law of gravity equation, pointing upward, and then you find the hypotenuse. And here's the deal, a squared plus b squared equals c squared. So that's all you're gonna do. You're gonna say a squared, which is when I plug my numbers through here, when I actually put the numbers in, you get 1.668 e to the negative 11 newtons. And if you're not familiar with big E, that just means times 10. And the b squared, that's this leg of the triangle, is the 6.67 e to the negative 11 newtons. Lost my newtons there. Sorry, I think you'd be disappointed in me. A squared plus b squared equals c squared. And I did the math, I hit equals, I took the square root, and I found out that c, wow, I'm really smearing today. The force gravity on ball 2, the net force, because we did the x direction and the y direction, we found the hypotenuse, the net force. I got about 6.88 e to the negative 11 newtons. And you're like, whoa, that's the force. Remember, force is a magnitude, so you also have to include the direction. If you want to find the direction, we have the opposite side of the triangle, we have the adjacent. So you're gonna do an inverse tan of this number divided by that number. So I just did it right here. Inverse tan of your purple number there is 6.67 e to the negative 11th divided by 1.668 e to the negative 11th, and you get like 75.96 degrees. And it might bug some people, like I rounded, but I went through and did my calculation not rounding, and I got about the same numbers. So that says force gravity too. I had a little whiteout issue. I was having some handwriting things. So I say that's how we do that. It's just what we've been doing. Step 1, draw a picture. Step 2, label our forces. Step 3, showed our coordinate system. We summed the forces in the x, we summed it in the y, and then we solved. We just did the math right there. If they ever wanted to find the acceleration, you know the mass of ball 2, you know the net force on it now, you know the mass of it. You could just take F equals ma. You know the F is that, you know the mass of ball 2 was 1 kilogram. So the acceleration is actually just gonna be 6.88 e to the negative 11 meters per second squared, just because the mass of ball 2 is 1 kilogram. So that's how you do that. And they'll show up there in concepts. Like they might say something like, they might want you to reason out, why does the purple ball exhibit more force than the blue billiard ball at the origin? And you're like, oh, why does that make sense? They have the same masses all throughout, but this separation is 1 meter, that's 2 meters, so this is gonna have 4 times the force as that right there. So if you were to check it, you'd be like, hey, if you took this number, the purple one, divided by that one, you're gonna figure out it's like 3.99, it's like 4 times the force. So it actually does work out, because being closer, you have more of a gravitational pull. That's a pretty normal question as an AP physics test, but usually it's more concept-based, so they might not give you numbers, they might have you reason some things out, like vector links and things like that, depending on the free response or what you're talking about in the test. So thanks for watching.